That's our last seminar. It's about some numerical aspects which in particular appear together with the nonlinear force density method, together with constraints. When we solve equations with or without constraints, the first question is, which are those equations? And the second, how are we solving those equations? And what technical issues have to be considered as a consequence, depending on the technique we apply. Of less importance is which solution method do we apply as long as we solve the right equations. The force density equations are not more than the equilibrium equations, and of course they may always be solved by alternative techniques. I've mentioned some of them in the previous seminar. For instance, we can take matrix methods or dynamic relaxation or what you like to do. Let's discuss the sequel first of all with this little example. You remember we have introduced that in the previous seminar, this 4-element cable net, where just the coordinates of the center node xc, yc and zc are the free variables, which means they are the unknowns which we like to solve for by form finding. We reformulate these three equations as displayed, where we just in particular have here the sum of the force densities of the 4 elements, just abbreviated by this notation sum of Q. Then you see we have collected everything what is in terms of these unknown coordinates x, y and z and something else. And what you see here, first of all, that's the definition of what we call the residual force vector, respectively its component in x, y and z direction. For this example we have only 3 unknowns, that means we have 3 equations, and therefore we have also 3 components of the residual force vector. For larger problems, the size of this residual force vector always is the size of the equation system. That means for every unknown free variable just have another equation, and it means another entry in this residual force vector. Here we have these 3 equations again on this slide. Let's just introduce more definitions. Though we can just put together everything here which is not a function of these coordinates here as what we call the components of the generalized load vector. You see it here on the right hand side. So in this case these are the components of the load vector, and here we just again collect those components in a vector. Next is that we identify these leading sum Q's here as components of what we call the stiffness matrix. In this very specific example here, the stiffness matrix looks like that. It's a 3 by 3 matrix, so the number of unknowns as columns and rows. And for this specific example, it's just filled up at the diagonal. That might be different for other examples. That makes it simpler here for this example, but that's exactly the entry in the stiffness matrix. And then we just may rewrite these 3 specific equations into a vector matrix equation which exactly expresses what we see above. So the product of the stiffness matrix with these entries on the diagonal times the vector of the free variables minus the load vector, that together is the residual force vector, is equal to 0. Or we may rewrite this system of equation equal like that. So this equation, what we have written here, is in general valid for arbitrary number of unknown coordinates. For instance, the coordinates of a finite element mesh, as I said already. So the size of x, the vectors r and f, and the size of the stiffness matrix is the number of equations, the number of unknowns. If we look at nonlinear equilibrium equations of fully nonlinear problems, for instance minimal nets, then the residual force vector is indeed a nonlinear function of x. We have seen in the previous seminar that these entries in the residual force vectors representing equilibrium stem from applying the virtual work, which should just disappear at the optimal solution. Then, solving these nonlinear equations, we apply the Newton-Raphson method, which in particular based off a Taylor series expansion. I have also introduced that already or commented it already in the previous seminar. By linearization, we have to linearize the residual force vector, which gives the nonlinear stiffness matrix, multiplied by the modification of the free variables in iteration step n, plus the residual force vector in iteration step n, sum up to P0, just representing the original nonlinear equation respectively. So a linear equation we can always solve in terms of the stiffness matrix, refer to the previous slide, now in iteration step n, and the load vector, refer to the previous slide, where R has been identified as the negative load vector. And then the Newton-Raphson iteration works like that. In iteration step n, we have the stiffness matrix, we have the load vector. From that, we just determine the update vector in X by multiplying the inverse stiffness matrix times the actual load vector. And then we can just update the vector of the free variables, that means the coordinates of the free nodes, just by adding to the actual state of free variables of step n, the update, and receive the free variables in the next step n plus 1. And we just start with n equal to 1 and just are iterating as long as necessary that the norm, as we say, of this update vector x is smaller than the accuracy what we take. So the norm is typically the Euclidean length of this update vector. That's a Newton-Raphson iteration. That means repeatedly generating these linear equations, which can easily be solved and repeating. What we just have seen in equations can nicely illustrate it in a graphical interpretation. Again, looking in this linear force density equation, k times x equal to f, with the stiffness matrix, the load vector, and the vector of unknown, where the stiffness matrix, as we just have seen, is quadratic, and in the original case symmetric and positive definite. That means that the determinant of the stiffness matrix is positive. That's the standard case of the classical force density method. Then the stiffness matrix may be interpreted as the system matrix of a quadratic function. Let's call it f here. It's quadratic, obviously, in x, and the linear term just comes together with the load vector. That might be a simple representation of the potential energy, however, in n dimensions. So if you just take 2 dimensions, x and y for instance, then the graph of a quadratic function just may look like that. It's a plot, let's say, with elliptic contour lines, where the solution, that means the minimum of this objective function, let's call it objective function, is just the minimum here of this function. And there exists only one solution, though we call it the global solution of the question, minimize this quadratic function. And then we can determine derivatives of this function, which is again a vector with as many components as dimensions, and again that gives the residual force vector in the interpretation of our equilibrium problem, just referred to above. Then the equilibrium r equal to 0 is of course identical with a 0 derivative. And that means this vector for our 2-dimensional example has 2 entries, derivative in x direction, derivative in y direction, and they are 0, both 0, just here at the minimum. That's always the standard necessary equation for identifying minima. And we call the vector of the solution at the minimum just x star, the so-called optimal solution. Little example here with k and f, and we solve this problem here. We just receive at the optimal solution x star at 0.5 and 0.5. Just refer to our little sketch here. And if we just refer to this nonlinear Newton-Raphson iteration, then we, as we have seen, repeatedly solve quadratic problems. What you see are the contour lines of a very famous function, the so-called banana function, which has been invented just to prove several things with optimization theory and optimization algorithms. It looks like that. And the strange thing, here's the minimum, a very flat function. Here is the minimum. And typically we take a start solution, an initial solution, where we just initiate our procedure. So what we're doing is that we just determine the stiffness matrix at this first iteration step, and we determine the out of balance load vector and can by that construct the quadratic problem as on the previous slide, which we minimize in one step. Here's the minimum point. That means the lowest point within this quadratic pot, and then we just repeat. So for next step, we just determine again a quadratic problem which have with elliptic contour lines, where here is the minimum of this next step. Then again, we construct a quadratic problem with elliptic contour lines, where the solution of our problem, that means the minimum of this quadratic problem, is now here. And then you see we repeat again a quadratic problem, we solve for the minimum, and by that the procedure is converging to the optimum step by step. That's what the Newton-Raphson method is doing, not more than repeatedly generating a quadratic problem, looking for the minimum, and repeat until we find the global solution of the nonlinear function, where again this solution is indicated by zero derivatives of this surface in n dimensions. Let's take a look here at this problem with these contour lines, and you see that's the case where we have three solutions, two minima, one here and one there, and a settle point here, where also in both directions the derivatives of this function just disappear, a horizontal tangent plane, let's say. Again, we apply Newton-Raphson at an initial point. We just generate our first quadratic problem. Here is our initial point, and the solution of this quadratic problem is just the minimum of this quadratic function. Then again, we generate a quadratic problem where we just find the minimum in the center of these elliptic contour lines, and we just repeat that until our algorithm is converging, and we just converge here at the first minimum as indicated here. And that's exactly the say a typical characteristic property of numerical algorithms, that depending from the initial point, now we start here, these algorithms are converging to the next local solution, in this case, where again the derivatives of the original function are disappearing. Let's start here. We generate our first quadratic problem, where the solution is the minimum of this quadratic problem. Then again a quadratic problem where the solution is the center of this elliptic contour lines, and if you just repeat, you see it also converges, but in this case it converges to the second minimum, which is now here with this optimal solution in terms of the x and the y component. And if we start here, again our procedure starts as always. It generates a quadratic problem where the solution is here at the center of this ellipse, and another one. And now it starts to identify that here at the global solution, the problem has not an elliptic property anymore, but a hyperbolic one. That means the solution is not at the center of the ellipsis, but at the center of this hyperbola. So, and still it may converge, or go on and converge, and finally it converges to the settle point here at the optimal solution, x equal to 0 and y equal to 0. So in principle, it's easy to understand what the Newton-Raphson method does, and the effort which just appears is repeatedly setting up this quadratic problem and taking the solution of this intermediate elliptic or hyperbolic problem. Let's introduce another idea, which is called the line search. So again, we just explain that with the quadratic problem. Here we have this quadratic function. Now Q is the system matrix, that what we in mechanics call the stiffness matrix. Nevertheless, you are now expert. You know that the quadratic problem we can just identify graphically as a function with elliptic contour lines, and the solution is the minimum of this elliptic pot if this system matrix is positive definite. So again, we start here with an initial solution. That's always necessary. Then we can first identify what is called the gradient of this objective function f. We call it f, the function here. The components of the gradient are the derivatives of the objective function f with respect to the three variables x. We can understand as a vector which is pointing upward in this function, upward on the steepest slope. That means if you have here the tangent to this point at this contour line, then this gradient is pointing in a direction lateral, perpendicular to the tangent. It's just like in the mountains. You are in the valley and you would like to climb upward, and you would take the shortest way to the summit. Then exactly you just always take the steepest slope. Or if you're thinking going downward, that's what is called as the steepest descent. So steepest descent means the steepest descent direction, just in opposite direction of the gradient. So that means, following the steepest descent down into the valley, you take S as a search direction, which is always the negative gradient of our function, which we would like to minimize. And we start here at the initial point k equal to 0, if that might be the iteration counter the k. So in steepest descent method means that we now follow this direction until we reach a point where in this direction this point is at the minimum. So if you follow this path, it goes downward, 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 until we just come to a contour line where this direction is again tangential, and behind this point you again just climb up the hill down there. So and that's exactly what we call the line search, just following the search direction until we reach the minimum, at least following this direction as we still follow a descent direction. From here on now it's not a descent direction anymore. Yeah, and the line search is just, in the ideal case, identifying this minimum. We indicate a path parameter which we call alpha, and starting from here we're adding a multiple of the search direction until we find the proper alpha where we just reach this line minimum. So, and then we repeat everything. Then again we just determine the gradient here at this point, take the negative of the gradient at the next search direction, follow this search direction until we reach the line minimum, and repeat again with determining the gradient, following the next direction until this thing just is converging to the minimum. That's a line search. And line searches we can use as an additional tool in completely nonlinear problems. Let's come back to our banana function. And we have seen before that we have arrived at this point to our iteration, and then the next quadratic problem were a little bit, let's say, problematic. It was very narrow here, and the next minimum of this quadratic problem was very far away. That's eventually we call overshooting. Then the method just starts to oscillate perhaps, or at least it is not really nicely converging anymore. And the reason really might be that the step might be far too large. And in particular, if we just follow this direction from here to there, you see the minimum in this direction might be somewhere there perhaps. And from there on, we are again climbing up our function. That means just deviating from the optimal solution. And there you see the line search might be added for every Newton-Raphson step just to stabilize what's going on. Here you see we have our search direction, and then our line search is just following this direction and checks if you are still going downhill, and eventually just reduce the step length as the next solution for the next generation of a quadratic problem. Though in a nice Newton-Raphson algorithm, it's not necessary to do this line search exactly to the line search minimum, but it's enough just to reduce the step to stabilize what's going on. And that's exactly what we are doing. We're just stabilizing our Numerical iteration eventually, just by adding a line search to make it more stable and reducing the step to the next intermediate solution. Now, let's consider the effect of constraints. So that's our original formulation, which in plain force density method is a quadratic problem, which may look like that, where we really indeed just have one unique solution, the global one, at the minimum of this quadratic problem in the center of the quadratic contour lines. If we now add constraints, and we just have seen, we're adding these by this Lagrangian technique, with adding to the quadratic energy term, this constraint term with these Lagrangian multipliers, then in terms of the free variables x and the Lagrange multipliers lambda, the function all in a sudden is a saddle function. It's not looking like that anymore, it looks like these. And the constraint solution is at the saddle point of this saddle function. That means we are not looking anymore for a minimum point, a minimum solution, but for a stationary point, that one, where again the derivatives in direction of the free variables and the derivatives in direction of the Lagrange multiplier just are zero. Yeah. We have seen another example before, yeah, with the saddle point. And the problem now is you just add line searches to a saddle function, then eventually it just depends on the direction. We will just follow this line search. There does not exist a minimum anymore, and it's just going down, go down, go down. And that means the line search may fail. And for strongly nonlinear problems, then we have to modify the line search technique to guarantee that in direction of the line search there really exists a minimum. And that means we are modifying this Lagrange function into what is called the augmented Lagrange function, just by adding to the Lagrange function this extra term, this penalty term, where we just take the constraint square and multiply it by a penalty parameter of finite size and multiply it by 1/2. So that's what we receive now is the augmented Lagrange function. It has this special property that at the optimal solution of the constraint problem, when the constraint is 0, this penalty term also is 0. Yeah? So it does not modify the solution in that case. And also at the optimal solution, the derivatives, the gradient of this penalty term also vanishes. That's another nice property. It's just modifying the curvature of our Lagrange function and neither the value at the optimal solution, not the derivatives at the optimal solution. That means taking the augmented Lagrange function as a function which we take for the line search. The solution will not be modified, only the intermediate solutions. Yeah, let's look what happens. So if you just look from above on our Lagrange function, it looks like this. These are the contour lines of a saddle point here, a saddle function, where here's the saddle point. Looking from the side here, you nicely identify the saddle function here with the stationary point, the saddle point. Here it is. Yeah, and if we now just take a look at the procedure as before, where we had an intermediate solution and would like to find the saddle point. So from here to there, that nice seems to be up and nice. But eventually, if you don't hit the saddle point and you just have a search direction which may look like this, then you see, as we just follow this direction here along this line search path, there is no minimum at all, and that means you can follow forever this direction. That's what we call an unbounded line search function, which does not the job. It will not reduce the search step, as we just have seen before. It will give you just nonsense results. So, and that exactly is the role of this penalty parameter here, that if we now increase this parameter, carefully, you see this line search direction, the line search function behind, which is this one, this augmented Lagrange function, starts to become what we call convex. That means with a positive curvature, where along this direction there indeed exists a minimum. And it depends on the penalty parameter. We further increase it and increase it and increase it, how much the step size might be reduced applying this line search technique. And by that you further may just stabilize your numerical procedure and can control the step size between two iteration steps. And that's exactly the effect. And you see as it just tend to infinity with the penalty parameter, then the function even seems to become single curved like a cylinder, where it's clearly obvious where the line minimum is in this case. But the nice property of this augmented Lagrange function, where we also have the Lagrange parameter, is that these penalty parameters must not be too large to be successful with this stabilization. Here we see a first example. So you see, we just try to do the form finding for this example here, and you see we have completely rubbish, and then we add a line search with the penalty parameter, and it nicely converges to the solution what we intended for this arch bridge with hangers. We have here the deck. Stabilization is when we use this augmented Lagrange function not only for the line search but also for the standard solution. Again, remember that is the Lagrange function of the constraint problem. That is the augmented Lagrange function which we use for line search with the penalty parameter, and the structure is identical, but nevertheless we use for the stabilization another parameter different from the parameter for the line search. This one for the stabilization of the original problem, which we call R sub S for stabilization, which we add to the Lagrange function for the standard solution, so that we can distinguish between stabilization of the original problem and the function which we use for line search only. And in general, we just take different numbers for the general stabilization and for the line search parameter. Here you see it in the latest version of STIF, that we have two entries with parameters like that. Here we have the stabilization parameter, that's this R sub S for the stabilization of the original problem. And if we just allow line search, we have another parameter which we call the penalty factor. That's this one, for using the augmented Lagrange function for line search only. Another example, well, that's the basic module of tensegrity structure, and we just try to find the optimal solution, the form find solution. You see, do nothing, we just start with plain and poof, no solution can't be found. And now we just add a little bit of a stabilization factor, and nicely the problem all of a sudden is converging to the optimal solution in 5 iterations with a quadratic convergence. So little add-on, and you have a very, very large effect, very nice effect. Then another subject, if we just go into negative force densities, here we have another problem here, and we just try to find the optimal solution for the structure with given force densities. In this case you see a negative one here, a negative one there. Here we have positive force densities, and as an effect, of course, that's what is the result of that. So we have here an arch in compression, which is just loaded, let's say, by these cables here in tension. And perhaps remember our previous example where on the stiffness matrix, on the main diagonal, we had the sum of the force densities of the cables at a certain node. If you just look, for instance, at this node here, at this node you have here a cable with force density -1, another one with -2. This adds up to -3, and we add the force density of this cable, which is 3. That means all of a sudden the entry in the stiffness matrix is 0. For these degrees of freedom. That's the same for degree of freedom number 2. Again, we have the same 3 elements where the force densities add up to 0. If you just look here at the degrees of freedom number 3 and 4, that's down there, 3 and 4, and then you see we have 4 elements, and they adding up to 3, 6, and these together also to 3, adding up in total to 9. That's the entry there. And for this node again, for degrees of freedom 5 and 6, we have again this fact that the force densities again are just summing up to 0 here. That is not nice, because quite a lot of solvers don't like that if there are entries of 0 on the stiffness diagonal. And then you, of course, you have to apply special solvers. And which is so far not a problem, that within the libraries you may find solvers which are able to handle that. Eventually, however, the system of equation might be kinematic. That means that the eigenvalues of a stiffness matrix like that may become 0, which is not nice. Then the system of equation can't not be solved. The structure is kinematic. We see in a second something what we can do against that. That was this grid shell example I've shown you already. And if you just apply loads like that, then we have negative entries in our stiffness matrix. It's not a problem here because all of the members are in compression. Then all entries are negative in the stiffness matrix, but there's no zeros on the main diagonal. But as soon as we just have members in compression, you at least should be aware that eventually it may appear this problem that the stiffness matrix may have 0 entries on the main diagonal or even kinematic, and then you have to think about special solvers. So singular stiffness matrices, it's exactly as I said, that we have 0 eigenvalues, or the determinant of the stiffness matrix might be 0, and then we can do the following. That we just look at our stiffness matrix and determine the 0 eigenvectors. They may look like that here, for instance, for this problem what we had before. We can stabilize the stiffness matrix just by adding the adiabatic product of each of these eigenvectors, multiplying that by appropriate scaling factor. Then we solve the problem and receive a modified solution, and the next step we just take away again that what we have added here as a stabilization, and just receive in a solution which gives us equilibrium in a kinematic problem. The question is, how can we get the eigenvectors? And there are quite nice procedures which we can just apply by the factorization of the stiffness matrix for our solution, where we still solve for a linear step. And that means it's no extra cost at all, or not a significant extra cost to determine these 0 eigenvectors. Then we just can modify this problem what we had before here, which is aligned at the benchmark from Schleich, Bergermann and Partner, where we just have this pedestrian bridge with an arch and a curved deck in a curved line. And I just show you now the success of all our techniques, together with self-weight here of the deck, together with controlled positions of these nodes. You would like to have a horizontal deck, also controlling the apex of this arch, and eventually also the length here of the deck element to be constrained. Let's take a look how this works. So just look at this apex point. There you see, here we have the control, the set control, the set coordinates, and you see that the elements of the arch are all referring to this control. And it's again a case where we just scale many elements by the same scaling factor. Then we have here the goal length of a member of the deck, putting to 2.5. Then another one also 2.5, and this one set to 2. And we now come to the the deck here, where we just have an element where we just refer that to the constraint number 7, where we just see the respective controls here of the node. This node is controlled by the force density of this element, and by that we can just, you see again here, the control Z coordinate is 0, and we just have the ID of the respective scaling factor in the highlighted element. So by that, we just have set up everything, and if we just go for the solution, and again it's not converging because still it's highly non-convex, then let's just try to add a little stabilization factor. Perhaps it's enough. Let's try it. Yeah, it's better, but still not good enough. And then let's come together with an extra line search. These are these two parameters I have explained. And then we just nicely solve the problem in 12 iterations, again with a quadratic convergence, rate of convergence, having extra 6 line searches. So every second step, let's say we have a line search, typically they are at the beginning of the iteration, and there we are. When you set up problems like this, which are highly nonlinear, we have these possibilities and the combination, and it's not a big issue just to try around with these factors. Typically they must not be very large. That's a nice effect of the augmented Lagrange function. We already arrived at the summary of the seminar. It was then you finding that the equations of the unconstrained original force density method are linear. We have learned that this is equivalent to minimize the quadratic function, which can be nicely illustrated by graphical means. And there we see readily that a quadratic function indeed only has one global minimum, and that is equivalent to the unique solution of linear equation systems. The equations become immediately nonlinear if you add constraints, and the iterative solution which we apply along the Newton-Raphson iteration technique is nicely understood as the sequence of minimizing quadratic functions. Moreover, if we just add constraints, we don't have an elliptic problem anymore, a quadratic elliptic problem anymore, but at the global solution, the function has a saddle function property. That means it is a hyperbolic problem, and therefore it might be tricky to find the solution numerically. For strongly nonlinear problems, the Newton-Raphson iteration might be stabilized, and we have different techniques, which all of them are just based on what is called the augmented Lagrange function, where we're just adding to the basic Lagrange function extra penalty terms with a penalty factor, where the constraint functions just appear quadratic. We may use this augmented Lagrange function extra, that means additionally to our basic problem with the line searches. Line search means that between two iteration steps we are interpolating the previous and the actual solution, just to control the step size between these iteration steps. We can use also this augmented Lagrange function directly by directly using this augmented Lagrange function for the basic solution of the Newton-Raphson iteration. Both approaches have their special properties, and just by trying around with the practical problem at hand, you will easily realize which one will help you. If we deal with mixed positive and negative force densities, which is the case, for instance, if you have arch bridge where the arch is in compression and you have hangers which are in tension, then it might happen numerically that eventually the entries on the stiffness matrix diagonal might be 0. That is eventually, and that makes it eventually necessary that you take a special solver, equation solver, which is able to tackle this problem, or this property, better to say it's not a problem. Eventually you may deal with kinematic systems. That may be the case, for instance, with tensegrity structures. then the stiffness matrices are singular, and they might be stabilized by making use of the dyadics of zero eigenvectors, which is not a problem to evaluate them, as they can just get them as a byproduct of the matrix factorization. But then we go very deep in details of numerical analysis, and I did not comment how to do that, but that's simply an information for you. And finally, when doing form finding of challenging practical problems, then it's a good idea to mix all the mentioned stabilization techniques simply by trying, giving numbers for the penalty factors, penalty parameters, and just observe what will be success. It's really a minimum of modeling effort, and when everything just converges quadratically, then it's also no time effort. That brings us to the end of the workshop. We had 4 very challenging seminars where we just treated a lot of aspects of the greater force density method in all directions and with many aspects. And I hope that you just liked also how I just presented it with my characteristic attitudes, which might be not always absolutely positive, but I tell you I had a lot of fun with preparing this seminar and preparing these records. At least it's valid for me. I really have deepest respect for the inventors, Klaus Linkwitz and Hans-Jörg Scheek, who just came up with this idea. And you see how inspiring it might be if we just follow these lines. Thank you very much. Be positive. Use and apply the force density method, and in case of questions, I'm always here. If I am able to answer your questions, I might be happy. Thank you very much. See you perhaps later on any occasion. Bye.